All right, good morning, everyone. So today we are going to dive deeper into the goodness of fit test for chi-square. We started this yesterday with the example on the PowerPoint, but we're going to continue with this today just because a lot of us were having issues with finding the expected value and then calculating the test statistic using the formula. So we're going to continue with this today. So first, let's just read the problem. In the game Rock, Paper, Scissors, Kenny expects to win, tie, and lose with equal frequency. So that is going to be important. Kenny plays Rock, Paper, Scissors often, but he suspected his own games were not following the pattern. So he took a random sample of 24 games and recorded their outcomes. And here are his results. So I know in the last sentence here it says to use a chi-square goodness of fit test, but again I just want to note why this is chi-square and not some other type of significance test. So here we're looking at again categorical data in terms of winning, losing, and tying. And we're doing each of those events and we are observing values. So again, since this is categorical data, since these are observed values, he did the test, played the game, here are his results, those are observed values. So I know that this has to be chi-square goodness of fit because we're looking at observed values in just one category of playing the game. So we can start with our hypotheses here. So for the goodness of fit test, our hypotheses are always going to be the same. The observed values are equal to the expected. The alternate is always going to be the same. The observed values are not equal to the expected. And I highlighted this part here about equal frequency, and that's exactly what the chi-square test is testing for. Are our observed values evenly distributed with what we expect? So looking at these, I need to determine whether or not I can actually perform the test based on the conditions that we talked about yesterday. So for our conditions, we need to make sure that we're taking the sample randomly, which it does say in the problem, took a random sample. We need to make sure we have a large count, so our observed values have to be greater than 5. So here, because technically the wins is not greater than 5, we don't meet this criteria. So at this point, I would actually stop the test and not even continue because my observed values all have to be greater than 5, and the observed values for the win is not greater than or equal to 5, so I actually can't do this test. I'm still going to perform this just so that we can see how the test would be conducted, but at this point, if this were an FRQ, I would actually stop right here because my conditions have not been met. The last one is just the independence, so this is the sample size of 24. So again, this is our n. Is 24 over, we could play the game so many times, so we can put this over, that was a terrible infinity. We can put this over infinity. So we know that this is independent. So again, it does not meet the large count, so we would actually not do this test, but here, for the sake of you understanding how to do the test, we're just going to continue. Third step here is to calculate our test statistic. So we need to calculate chi-squared. And so that was the formula we did yesterday. So the sum of our observed values minus the expected quantity squared over our expected value. So many of us were having some trouble yesterday calculating the expected value. So I want to just go over how to do that in this lesson just so that we're all on the same page. So because we are looking at equal frequency, we would expect these to be distributed equally. So we would expect to win, lose, and tie equal times. So we play the game 24 times. So n is 24. And there are 3 possibilities here, 3 possible outcomes. So k is 3. So to find the expected value, we're going to take 25 and we're going to divide it by 3. Or excuse me, 24. Let me fix that. 24 was our n value. So 24 over 3, and that's going to give us an expected value of 8. So we would expect to win, lose, and tie 8 times each. So using that value, that's going to be the same for every single one of these. So my chi-square is going to be equal to the first observed value. So I'm starting with the first value in the table, 4. He played the game and he won 4 times, so that's the observed, minus the expected. So we just calculated we would expect to win 8 times. And then it's a summation, so I keep adding the next value in the table, 13 minus 8, quantity squared over 8, plus the next value in the table, 7 minus 8, quantity squared over 8. And that is going to give me 5.25. And that's my chi-square test statistic. I'm not going to take the square root of this value. It should be a squared quantity. So do not take the square root of your test statistic. That is your final test statistic. I don't need to take the square root.